In this session, we are going to talk about the derivative and the topics that we have in differentiation. As we know that differential calculus deals with the study of the rate at which quantity changes, so it has many applications in all disciplines. For example, in physics, the derivative of displacement with respect to time is called the velocity, and the derivative of velocity with respect to time is called the acceleration. In a simple word, we can say that the process of finding derivative is called the differentiation. So we are going to learn about the derivative and the techniques that we have in differentiation. Besides this, we need to know the formulas of differentiation. So you can see that the formulas are here. So these formulas will be useful always. So before talking about derivative, we need to know about tangent line and secant line. So what is tangent line and what is secant line? First of all, if we try to understand the definition of tangent line, then you will see that tangent line is nothing but a straight line. We know from the concept of geometry that any straight line can be written in the form of y equals mx plus c. So this is the standard form of a straight line. We can also think about ax plus by plus c equal to 0 as the general form of a straight line. In some textbook, you will see the straight line is in this form, ax plus by equals c. We have also another form of a straight line, that is x over a plus y over b equals 1. So this is also the form of a straight line. But the standard form is this one, y equals mx plus c, where m denotes the slope. So now we need to know about what is slope. C is the y-intercept. So besides these equations, we also know that if a straight line goes through a point x1, y1 with a slope m, then its equation will be y negative y1 equals m times x negative x1. We also know that if a straight line goes through 2 points, say x1, y1 and x2, y2. So in that case, if we try to find the slope, so slope will be y2 negative y1 over x2 negative x1. So whenever we need to find the tangent line to any curve y equals f of x at any point x1, y1, then this formula will be helpful. So the definition of tangent line says that tangent line to a curve at a single point is the straight line that just touches the curve at only a single point. So you will understand from here. Suppose we have a curve. Let's say the point P is on the curve. So we can think about a straight line that touches the curve only at P. So let's say the coordinates of P is x and y, or we can say x1, y1. So this straight line is called the tangent line. Let me draw another curve. This time, suppose we have 2 points. one is P and another one is Q. So if we join these 2 points, we will get another line. So this line is called the secant line. And the coordinates of P is x1, y1 and Q is x2, y2. So you can understand that tangent line is the straight line which touches the curve y equals f of x at only a single point. But the secant line is the straight line which touches the curve y equals f of x at 2 points. The points are distinct. P and Q are different points. So for simplicity, we say that tangent line is the line which touches any curve at a single point. Secant line is the straight line which touches a curve at two distinct points. P and Q are different points. So we can think about tangent line also here. This is a line and it touches the curve at a single point. We can also think about another tangent line. Let's say this is touching the curve. So this is also a tangent line. We can also think about another tangent line which touches the yellow colored curve. So all these straight lines are called tangent line because all these lines are touching at a single point. Suppose for this curve y equals f of x, we have 2 points P and Q. By joining P and Q, we have found a line. That straight line is called the secant line. We can think about tangent line here also because this line is touching the curve at a single point. So now we can understand that tangent line always touches any curve at a single point. Secant line touches 2 points. So why do we need secant line and tangent line concept? Because the definition of derivative deals with secant line and tangent line. So we'll not go into the details of the definition of derivative, but for now, we are just trying to understand what is tangent line and what is secant line. So let's say we have a line in Cartesian coordinate system. We have xy plane. It is called xy plane or Cartesian coordinate system, x-axis, y-axis, positive x, negative x, positive y, negative y. So this plane is called xy plane. Suppose we have a straight line here that is in the form y equals mx plus c. So we need to understand what is the slope of this line. So we need to know how we can evaluate the slope. Already we have learned that this m is the slope. But from the concept of geometry, you know that slope can be found by tangent of theta. So there is an angle here from positive x-axis counterclockwise to the line. We have an inclined angle. So based on that angle, we can say what is the slope of that line. The angle that we see here, that can be acute angle, that can be obtuse angle. So what is acute angle? The angle that is greater than 0 degree but less than 90 degree, that is called acute angle. What is obtuse angle? The angle that is greater than 90 degree but less than 180 degree, that is called obtuse angle. If the angle theta is 90 degree, then we say it is right angle. So you have to understand that angle can be classified into these two categories mainly, acute angle and obtuse angle. So suppose we are going to evaluate tan of 30 degree. So we know that in Cartesian coordinate system, this is the first quadrant, it is the second quadrant, it is the third quadrant, and this one is the fourth quadrant. First quadrant, second quadrant, third quadrant, and fourth quadrant. In first quadrant, all the trigonometric forms, that is sine theta, cosine theta, tangent theta, cotangent theta, secant theta, cosecant theta, all these are positive. In second quadrant, sine theta is positive, cosecant theta is also positive. But we are dealing with tan theta for now. So we know that on third quadrant, tan theta is positive. But what about the behavior of tan theta in second quadrant? That means suppose we have a line here and the angle that we see, let's say it is 150 degree. So let's try to find tan of 150 degree. So it will obviously be negative. You can check. So tan theta, that is tan 150 degree, is negative 1 over root over 3. So you see that we are getting negative values. So let's try with another angle from first quadrant. Let's say tan 30 degree. That means the angle that we have is in the first quadrant. So it is about 30 degree. So let's try to figure out what is the value of tan 30 degree. So it will always be positive because in first quadrant, sine theta, cosine theta, tan theta, and cosecant theta, secant theta, cotangent theta, all that are positive. So in that sense, we can say tan theta is also positive. But we have our calculator. It is easy to find. We are targeting for the value of tan theta. If theta is acute, that lies in between 0 to 90 degree, then obviously the result will be positive. If the angle is obtuse, that means it is greater than 90 degree but less than 180 degree, then be sure that tan theta will be negative. So we know that tan 30 degree is 1 over root 3. So we are getting positive values. Again, we have the x-axis and y-axis, that is the xy plane. So suppose we have a line here. First of all, we need to understand what is the slope of that line. Let's say we have another line here. We need to understand what is the slope of this line. So how we can understand what is the slope of any line that is of the form y equals mx plus c? So this is by checking the angle. If the angle is acute, then slope will be positive. That is, slope means m, that is tan theta will be positive. If the angle is obtuse. Angle means the value of theta from positive x-axis to the line. So if the angle is obtuse, slope will definitely be negative. That means slope means the value of m, which is equal to tan theta, that will be negative. So for the first line, I am denoting this one as line 1 and the second one as line 2. So for the first line, let's draw an angle from positive x-axis to the line. This is positive x-axis. We are coming from counterclockwise direction. So we can easily understand that the angle that we see here is less than 90 degree but greater than 0 degree. So obviously the slope of the first line will be positive. That means the value of m will be positive, or slope will be positive for the first line. Let's draw an angle from positive x-axis to the second line. So automatically we can understand that this angle is greater than 90 degree but less than 180 degree. So obviously the slope of this line will be negative because the angle this time is obtuse. The angle that we have is greater than 90 degree but less than 180 degree. So let's try to remember or recall the values of tan theta because it is important. 0 degree, 30 degree, 45 degree, 60 degree, and 90 degree. So we know that tan theta, that is tan 0 degree, is 0. Tan 30 degree, 1 over square root of 3. Tan 45 degree is 1. Tan 60 degree will be root over 3. And we obviously know that tan 90 degree will be undefined. So in that case, we say that tan 90 degree, it is undefined. So suppose we have a line in xy plane. The line is just like this one. This is our straight line, which is parallel to the y-axis. So we want to find the angle from positive x-axis to the line. So we can understand that the angle will be just 90 degree. That means the angle is right angle, which is 90 degree. So in that case, what will be the value of slope? Let's try to find. We know that the formula for slope is m equal to tangent of theta. So tangent of 90 degree, we are plugging the value of theta. So tan 90 degree is undefined by using this concept. So we have found m equal to undefined. So we say that the slope for the vertical lines is undefined. That means the line that we have has an undefined slope. Slope is undefined. Similarly, let's try to check another line. Suppose we have the xy plane, and we have a line that is parallel to x-axis. Whatever line we have previously here, that line is parallel to y-axis. So in that case, we are getting undefined slope. But when we have a line that is parallel to x-axis, at that time, what will be the angle and what will be the slope? So we can understand that this line has angle 0 degree. Okay, so in that case, the slope will be m equal to tan theta, that is tan 0 degree. So we know what is the value of tan 0 degree. It is 0. So we have m equal to 0. That means the slope is 0. So for these horizontal lines, slope will be 0. That means it is called 0 slope. So remember, the vertical lines that we see here can be denoted by x equal to a. So whenever you will see x equals a, that will denote vertical line. Whenever we have the horizontal lines, it will be denoted by y equals b. So these are called horizontal lines. So besides y equals mx plus c, we can think about x equals a. We can think about y equals b. So y equals mx plus c is a straight line that has a slope m, which is inclined with 0 degree, or let's say 30 degree or 50 degree or 150 degree or 180 degree, like that. It depends. So slope can be anything. But specifically for this case, x equal to a, we have the vertical lines. So in that case, slope will be undefined. Whenever we have y equals b, slope will be 0. So these are called horizontal lines. So at that time, we will get 0 slope. So in general sense, we can say, in summary, suppose we have a line here, the slope will be positive. If we have a line here or here, the angle is looking greater than 90 degree and less than 180 degree. In that case, slope will be negative. Suppose we have a vertical line, slope will be undefined. Suppose we have horizontal lines, slope will be 0. So in Cartesian plane, in xy plane, you can understand by this. So we are talking about tangent line. So for tangent line, we need to understand about the straight line. That's why I have described these concepts. So there is a relation between tangent line and the definition of derivative. So for that, you need to know the concept tangent line. Tangent line is a line which touches a curve at a single point, and that will follow y equals mx plus c. So tangent line can be found for this curve y equals f of x if we try to find the derivative of that curve at any point x1, y1. So dy dx is called the derivative of this function. We will get f prime x. So this will denote the slope m. So whatever we have seen previously, that m equals tan theta, but for now we have understood that m can be found by the derivative dy dx at any point x1, y1. So this is the relation between derivative and slope. So I hope you have understood the definition of tangent line and secant line. And whenever we have to find the slope of the tangent line that will be equal to the derivative dy dx at that point. So this is the time to focus on the definition of derivative. Suppose we have a curve with 2 points P and Q. So whenever we are joining these 2 points P and Q, we are getting a line. That line is called the secant line. So P point has the coordinate x1, y1 and Q point has the coordinate x2, y2. So we can understand that this distance is y1 and this distance is x1. Similarly, this distance is y2 and this distance is x2. If we try to collect this distance only from this part to this part, it will be x2 negative x1. If we try to find this distance only, so it will be y2 negative y1. That means we are finding the difference between y's, that is y2 negative y1. The difference between x2 and x1 will be x2 negative x1. So for now, suppose what will be the case if Q comes closer and closer to P? Suppose Q point is here, then the secant line will be here. The Q point is also here. The secant line will be here. Q point is here now. There will be also a secant line, but there will be a certain time when Q and P will be as near as possible. That means Q will be approaching to P. At that time, this distance, the distance that we have, x2 negative x1, will be x2 negative x1 will tend to 0. That means, let's say, y2 negative y1 is delta y, that is denoting the small change of y, and x2 negative x1, in short, let's say it is delta x, a small change in x. So in that case, delta x will be 0, will be approaching to 0 whenever Q is approaching to P. So at a certain time, Q point and P point will coincide. And at that time, the secant line that we had previously will be the tangent line. And we know tangent line is the line which touches at a single point. So we will get a certain situation whenever the secant line will be the tangent line. So whenever we will get this type of criteria, at that time we say that is the instantaneous rate of change between y over change between x, and that is the definition of derivative. So derivative deals with the rate of change with one quantity and another quantity. So delta y over delta x will be dy dx if we take the help of limit delta x tends to 0. So that's why now we say that dy dx is limit delta x tends to 0, y2 negative y1, x2 negative x1. For x2 negative x1, we can write delta x because here we have written x2 negative x1 as delta x, this distance. So we can say limit delta x tends to 0, y2 if we have y equals f of x, y1 will be f of x1, y2 will be f of x2. So instead of y2, we can write f of x2. Instead of y1, we can write f of x1. So we are getting f of x2 negative f of x1. That is the same as y2 negative y1. And let's say x1 and x2 are written as x1. So x1 is x1 just like previously. But x2 is written as x1 plus delta x. So we can write just like this. Similarly, y2 will be y1 plus a small amount of y, that is delta y. So what we can write? We can now write limit delta x tends to 0. Instead of x2, we can write x1 plus delta x. And here we have x1. So this is the definition of derivative. And it is coming from tangent line. So in short, we can make it like this. It is easier to understand. Let's say delta x is ace. So we can write limit ace tends to 0 function of x1 plus ace negative function of x1 over ace. Why not we write x1 as x? Then it will be easier to denote. So we have finally dy dx equals limit ace tends to 0 function of x plus ace negative function of x over ace. So this is the definition of derivative. Using this definition, we can prove any formulas. So you can understand that the definition of derivative comes from the concept of secant line and tangent line. Secant line deals with the average change and tangent line deals with the instantaneous rate of change. So this is the introduction to derivative, and now we have to know what topics we have in differentiation and the techniques of differentiation. But before that, let's have a look on some functions. So suppose we have explicit function, we may have implicit function, we may have logarithmic or exponential function, we may also have parametric function. So we need to understand what does it mean by explicit function, implicit function, logarithmic function, exponential function, and parametric function. We also have inverse trigonometric function, but if you have a good control over these functions and you know how to find the derivatives of these functions, then it will be also easier. So for now, let me show you the forms that we have for explicit function. Explicit functions are in this form: y equals f of x. That means in left side we have y, on right side we have a function of x. So we can easily keep y in left side, and on right side we can have any sort of x type function. So this is called explicit form. What is implicit form? Let's say we have f of x comma y equals 0. From explicit function, you can understand that x is the input and y is the output. X is the independent variable, y is the dependent variable. That means y depends on x. X is input, y is output. Y depends on x always. But sometimes we will have f of x comma y equals 0. So that form is called implicit form. It will be difficult to keep y in left side and transfer all the x on right side. So sometimes it will be difficult. So how can we find the derivative if we have an implicit function? Logarithmic or exponential function. Suppose we have the form y equals f of x to the g of x. F of x has the exponent g of x. F of x is a function. G of x is also a function where x is the variable, just like y equals x power sine x. You can see x is a variable, and in upper part, in the exponent, we have also sine x. We have also x involved. So these are called logarithmic or exponential functions. But if we have y equals x squared, you can see x is variable that is going with f of x, but the exponent or power is just a constant. So we can easily solve by this explicit form, y equals x squared. It is going with y equals f of x. So you have to understand which functions are explicit, which functions are implicit, which functions are exponential or logarithmic. And then we have one important notation here, that is parametric function. So what is parametric function? For now, try to note down that we have x as a function of t, y is a function of t. So we have both x and y. Both x and y are functions of t. So in that case, we need to understand how to find the derivative. What is inverse trigonometric function? Suppose we have y equals sine inverse x, y equals cosine inverse x plus 1. So we need to know how to differentiate these functions. But before, you need to understand, if we have explicit function, how can we find dy dx? If we have implicit function, how can we find dy dx? If we have logarithmic function, what is the procedure to find dy dx? If we have parametric function, what will be the case if we need dy dx? So these are the important things. So suppose we have y equals f of x, then the first derivative is denoted by dy dx. Second derivative is by this one. Third derivative is by this symbol. And if we use prime notation, the first derivative of f of x will be denoted by a prime x. Second derivative will be a double prime x. Third derivative will be a triple prime x. Similarly, fourth derivative will be by this symbol, and fourth derivative of x. Here you can see that I have written 4 in the parenthesis. So that denotes the order of the derivative. How many times you are going to differentiate. We have also alternative notation. We can think about it is y prime. Second derivative is y double prime. Third derivative is y triple prime. Fourth derivative is y fourth. So we can also write this one as y1, y2. Third derivative can be y3. Sometimes you can also write this one. This will be comfortable for us. So these are the notations for derivatives. First derivative, second derivative, third derivative. But normally we use dy dx, d squared y dx squared like this. f prime x, f double prime x, y prime, y double prime. So you have to know all the notations that we use in differentiation. And now let's come to the techniques or rules that is applicable in differentiation. So the first rule says that derivative of any constant is 0. If we differentiate any constant, let's say 10, it will be 0. If we differentiate 100, it will be 0. If we differentiate negative 205, it will be 0. In general sense, we can say derivative of any constant will be 0. So this is the first rule. Then you can see we have here f of x plus g of x. We may also have the subtraction f of x negative g of x. So it says that the derivative of a sum is the sum of the derivatives. The derivative of the subtraction is the subtraction of the derivatives. Similarly here, derivative of a quotient can be found by this formula. So let's write down the rules here for our betterment. The first rule that you understand, ddx of a constant is 0. But ddx of, let's say we have u plus v. Instead of f of x and g of x, writing u and v will be easier for you to understand. So derivative of the summation u and v will be derivative of u plus derivative of v. And the same property holds for subtraction. Derivative of u negative v will be ddx of u negative ddx of v. ddx of u times v. We have a product. So how can we find the derivative if we have a product? So we have to know how we can find the derivative. It will be by this way. U ddx of v plus v ddx of u. So this is known as product rule. Whenever we have ddx of u over v, that means we have now a quotient. So it is called quotient rule. Please do remember here that the denominator can't be 0. If the denominator is 0, so something by 0 will be undefined. ddx of u over v, whenever v is not equal to 0. At that time, how we can find the derivative? It will be by this way. In denominator, it will be v squared. In numerator, v ddx of u negative u ddx of v. So v ddx of u negative u ddx of v over v squared. So this is called the quotient rule. And now we have to understand what is the chain rule. So chain rule mainly deals with composite functions. Suppose we have y equals f of g of x. Previously, we had just x here. Inside the parenthesis, we have the letter x. Now, we have g of x. So whenever we have f of g of x, this type of functions are called composite functions. It is often denoted by f composite z. So in that case, our target is to find the derivative dy dx. So we use chain rule. We consider that g of x as u. Then we will get y equals f of u. So dy dx can be found by dy du du dx. So this is called the chain rule. That means you have to find the derivative of a composite function. So in that case, the derivative dy dx can be found by dy du dx. But whenever we will solve some problems where chain rule is applicable, I will try to solve directly so that you can find the derivative quickly. So up to now, whatever concepts we have, with these concepts, let's try to solve some problems. Let's say we have y equals x times sine x. So how can we find the derivative dy dx? So this is our target. So you can understand that we have u and v. It doesn't matter if we consider this is u and this is v. Same formula can be applied. So we know ddx of u times v is u ddx of v plus v ddx of u. So let's consider this is u and this is v. So u ddx of v plus v ddx of u. So now you need to know the formula of the derivative of sine x and how we can differentiate x. So before this derivative, we have x. So it is just like before. Derivative of sine x, we know the formula. That is derivative of sine x is cosine x. So it will be cosine x plus we have sine x here. So we are writing as it is before. Derivative of x, it is going with ddx of x power n, and the value of n is 1. So we know that n x power n minus 1, that is 1 times x power 0. So anything power 0 is 1. So in that sense, it is 1. So ddx of x is 1. So finally, we have found our first derivative. So this is dy dx. So you can understand that the function that I have started with, it is of the form y equals f of x. And whenever we have y equals f of x form, this is called explicit function or explicit form. Similarly, let's try to solve another problem. Suppose this time we have y equals x plus 1 over sine x. So I am starting with some easy problems so that you can understand the concept. So here, again, our target is to find dy dx. So ddx of x plus 1 over sine x. So it will be ddx of u over v. So in denominator v squared, in numerator v, ddx of u, negative u, ddx of v. So this is called the quotient rule. And remember, the denominator can't be 0. So in that case, the restriction that we have, sine x, that is the denominator, is not equal to 0. So let's try to solve this derivative. We can consider the numerator as u and the denominator as v. So the result will be v squared, that is sine x squared. Sine x is considered to be v, so v squared, sine x squared. Then in numerator v, so sine x ddx of u. So our u is x plus 1. Then negative is coming. So negative u is x plus 1. Then ddx. So ddx of v is sine x. So we will get our desired answer if we solve this one. So here in denominator we have sine x squared, so we can keep the same thing here because we don't have ddx before sine x squared. So whatever quantity we have in denominator, we are writing the same thing. In numerator, we have sine x. Now, ddx of x is 1. ddx of 1, ddx of any constant is 0. Negative. Here we have x plus 1. So this is x plus 1. ddx of sine x is cosine x. So in left side we have dx, dy dx, dy dx. So now we can see that the result that we have found, sine x times 1 is sine x, negative x plus 1 cosine x over sine x whole squared dy dx. So this is how we have found dy dx, that is the derivative of the function, which is of the form y equals f of x. This is in explicit form. In the final part, we don't have any ddx here, so this is our final answer. So this is what we know as the quotient rule, and the previous one is the product rule. Let me discuss about the chain rule. Let's say y equals sine x plus 1, and we need to find the derivative of this function. It is in explicit form, y equals f of x. So whenever we are differentiating y, we have ddx of sine x plus 1. But for now, try to recall that we just know the formula of derivative of sine x is cosine x. But we don't know about the formula, what will be about sine x plus 1. The derivative of sine x plus 1 is unknown to us. So you can see that sine x plus 1 is another function. Let's say f with g of x. And we are going to find the derivative of this function. So in that case, I have mentioned that we have to apply chain rule in order to find dy dx. It will be found by this way, dy du, if we consider gx as u, and du dx. But things will be complicated if you try by this way. But for now, the process I am going to use here, that is also chain rule invisibly, but it is a quick process. Let's try to do by this way. For now, suppose we know the derivative of sine x as cosine x. So we can think about x plus 1 as x. So say we have x only. Derivative of sine x will be cosine x, and don't forget that we have x plus 1. So whatever we have considered, that should be again in differential form. So we have considered x plus 1 as x. So derivative of sine x is cosine x, done. But the full part will be completed if we differentiate the second part again, and both of these two will be in product form, in multiplication form. So this is how we can find. You will understand if we solve some more problems. So cosine x plus 1, and now you know the derivative of x is 1. derivative of 1 is 0. So we have finally cosine x plus 1. This is the final result. So we have y equals sine x plus 1, and by chain rule, we have found its derivative. Let's say we have y equals natural log of e power x. So what will be the case for this one? If we try to find dy dx for this, that is ddx of natural log of e power x. So we know that ddx of natural log of x is 1 over x. We know this formula only. But here we can see there is a term e to the power x. So we can apply chain rule. It is not going with the direct formula, but we can use the same formula. How? By using the concept that I want to mention here. That is, we know the formula derivative of natural log of x. So think about e to the power x as x, capital X. So natural log of x, its derivative will be 1 over x. So natural log of e power x will be 1 over e power x. And the term that you have considered will be again in differential form. So this is what chain rule says. So now we can simplify 1 over e power x. So derivative of e power x, you know, it is e power x. So e power x and e power x will be cancelled. Finally, we will get 1, that is dy dx. Let's say we have y equals 2 power tan x. We know that ddx of a power x is a power x natural log of a. So by this, ddx of 2 power x will be 2 power x natural log of 2. So we know this formula. But in the main formula, we have x. But here, what do we see? We have tan x. So let's consider it is a big X. So dy dx will be ddx of 2 power tan x. So we are considering tan x as single x so that we can apply this formula. So let's apply 2 power x, and the derivative will be 2 power x natural log of 2. So it is done. But don't forget that we have considered this one as x. So it should be again in differential form. So this is the thing what we know as chain rule. So finally we are getting 2 power 10x natural log of 2, and here derivative of tan x, you know the formula, it is secant squared x. So finally done. Let's talk about another similar problem so that you understand chain rule clearly. Suppose we have y equals cosine x cubed. So we need to find the derivative dy dx, that is ddx of cosine x cubed. So we know a formula, that is derivative of cosine x is negative sine x. This is known to us. But in the main formula, we have just x. But in the problem that we have, it is x cubed. So what we can say? X cubed can be thought to be x. So derivative of cosine x is negative sine x. And the term that we have considered as x, that should be again in differential form. So negative sine x cubed. Derivative of x cubed, you know, it is 3x squared. So finally done. So I hope you have understood what is chain rule. So here, now we have to understand how to find the derivative if we have implicit function. So the derivative of implicit function is known as implicit differentiation. So we have to know what is implicit differentiation. For now, let me take one function. Suppose we have x cubed plus y cubed equals 3xy. So this is defined implicitly. So let us recall what is explicit form and implicit form. Y equals f of x is the explicit form. And if we have f of x comma y equals 0, that is the implicit form. So whenever we have the explicit form, we can easily differentiate. That is, we are differentiating both sides, dy dx. And on right side, we are getting f prime x. So in that case, we have to use all the rules like summation rule, subtraction rule, product rule, quotient rule, or we have all the formulas. And just now we have learned what is chain rule. So all these things can be applied to find the derivative dy dx. But sometimes there will be some functions where we can't write y in left side. It will be quite impossible to keep y in left side and bring all x on the right side. So it will be quite difficult. So what will be the case if we try to find dy dx if we have the implicit form? Just like this one, if we try to solve this equation, x cubed plus y cubed negative 3xy equals 0. If we try to keep y in left side, so let's try to do y cubed negative 3xy equals negative x cubed. So y is factored out. We have y squared negative 3x equals x cubed. So we just need to keep y in left side. But on right side, we should have all x. But what we see here, on right side, we have again y squared. So that means we are unable to keep y only in left side, and on right side, we can't write a function for x. So that is a problem. That means the function that we have is described in implicit form. So if we try to find the derivative of implicit functions, so we have to be very careful about y. We know that y equals f of x. So if f is a function of x, x is input, y is output. After inputting x, we will get y. So y is totally dependent on x. That means we can also write y as y of x. So this is the concept what we will use here. And again, you will see that chain rule can be applied. So the function, this time what we have, it is implicit function. So f of x comma y equal to 0 is called the implicit form. So the function that we have, it is in implicit form if we transfer the right side quantity in left side. So we have now combination of x, y in left side and the right side is 0. So this is how we can construct the implicit form. So now our target is to find the derivative of implicit functions. So how can we do that? Remember, at that time, we have to differentiate both sides. So we are differentiating both sides. Our target is to find dy dx anyhow. So now we know that we can separate these summation terms because x cubed plus y cubed is here. So derivative allows us to separate the summation terms. ddx of u plus v is equal to ddx of u plus ddx of v. Using that property, we can separate. So ddx of x cubed, ddx of y cubed. On right side, we have 3xy. We can pull out 3 before because 3 is constant. But for now, let's say we can think about 3x as u and y as v. So on right side, we have u times v. We have the product rule here. So let's write ddx of 3x times y. Now, derivative of x cubed, you know, it is 3x squared. Similarly, we can find derivative of y cubed, but be careful about the symbols. Whenever we have differentiated x cubed, we are differentiating x cubed in terms of x. Here x and x are same. So differentiation of x cubed is 3x squared. But what will be the case for differentiation of y? Remember, y is not a constant. If we differentiate a constant, it will be 0. Inside y, we have x. But we are writing only y. But don't forget that we have y of x invisibly. Y is still a variable. So we can apply chain rule. That is, differentiation of y cubed. Now consider y as x. So x cubed, derivative of x cubed is 3x squared. So derivative of y cubed will be 3y squared. And the term that we have considered as x should be again in differential form. So whatever term we have considered as x, it will be differentiated again. That is the concept what we have learned just before this problem. So we have considered x cubed as x, derivative of cosine x is negative sine x, and the term that we have considered, that is again under differentiation. So it is chain rule. So implicit differentiation says that y is not constant, y is variable. So differentiation of y cubed will be 3y squared, obviously, but ddx of y will be here also because we are considering y as x. So differentiation of x cubed, 3x squared, and differentiation of x again. So this is the chain rule. On the right side, we have u times v. So let us consider 3x as u and y as v. So we know the product rule, that is, if we have ddx of u times v, so it will be u ddx of v plus v ddx u. So if we apply the product rule here, then u ddx of v plus v ddx of u. So this is how we have expanded the previous part. You can see from here, so differentiation of y is written as dy dx. ddx of y is dy dx. So we can write like this. 3x squared plus 3y squared, we have ddx of y. Remember, it is dy dx equals 3x ddx of y again. It is dy dx plus here we have y. Now differentiation of 3x, it is just 3. If you want to have the explanation, I can explain here. 3 is constant, so 3 is pulled out, and then we have the derivative of x. So differentiation of x is 1. So 3 times 1 is 3. So it is how we have found 3. So finally, we can reach to a conclusion that we have 3x squared plus 3y squared dy dx, 3x dy dx plus 3y. So our target is to find dy dx. What we can do? We can just group all the terms from left and right side where we have d dx. So here we have dy dx, dy dx. Our target is to find dy dx equal to what? So let's group. So we are keeping this term in left side, 3y squared dy dx, negative 3x dy dx. On right side, we are keeping 3y and we are transferring this term on the right side, negative 3x squared. So now dy dx can be factored out. So dy dx times 3y squared negative 3x equals 3y negative 3x squared. So from here we can write dy dx equals 3y negative 3x squared over 3y squared negative 3x. So we have found dy dx. This is our result. If we want, we can also simplify this one. That is, we can factor out 3. So we have 3 times y negative x squared, and in denominator we can also factor out 3. So y squared negative x. So finally the simplified form is y negative x squared over y squared negative x. So this is what dy dx. We have found our result. That means we have found the derivative of the implicit function. The implicit function that we have, it is x cubed plus y cubed equals 3xy, and the derivative dy dx has been found. It is y negative x squared over y squared negative x. So for now, let's say besides finding the derivative, we need to find the tangent line to this function at any point 1.5, 1.5. The question may be find the tangent line to the curve x cubed plus y cubed equals 3xy at any point 1.5, 1.5. So you know that tangent line is a straight line that touches any curve at a single point. So the point is given. So for now, let's try to understand what is the graph of this implicit function. So you can see that x cubed plus y cubed equals 3xy looks like this. And we are asking for the tangent line at 1.5, 1.5 point. So 1.5, 1.5 will be here. So there will be a tangent line. So let's see what happens. So the procedure of finding tangent line to any function at any given point is, at first we need to find the first derivative dy dx. The function may be explicit, implicit, logarithmic, exponential, parametric, or inverse trigonometric. That doesn't matter. But first, we have to find dy dx. We know that a straight line with slope m that goes through x1, y1 point can be defined by y negative y1 equals m times x negative x1. Whenever we have started our session, I have written this equation. Here, 1.5, 1.5 is, let's say, x1, y1. So the value of x1 is 1.5, the value of y1 is 1.5. So we know that m equals dy dx at any point x1, y1. This is the relation between slope and derivative. So from that concept, we can easily understand that we have to find the slope. And we have the value of x1 and y1 in our hand. x1, y1, you can see 1.5, 1.5. So now let's find dy dx at 1.5, 1.5 point. So at x1, y1, we can write dy dx as y1 negative x1 squared, y1 squared negative x1. That means where we have x, we have plucked x1, where we have y, we have plucked y1. So now at 1.5, 1.5 point, dy dx will be 1.5 negative 1.5 squared. Here 1.5 squared negative 1.5. That means in this equation we have just plugged the value of x1, y1. x1 is 1.5, y1 is 1.5. So if we calculate this, we will get negative 1. So that means dy dx at 1.5, 1.5 point becomes negative 1. This is the value of m. This is what we know as slope. So the tangent line is y negative y1 equals m times x negative x1. So just we can input whatever we have in our hand. So y1 is 1.5 equals m is negative 1. Here x negative x1 is 1.5. So now we can simplify this and we can move to y equal to mx plus c. That is the standard form of a straight line. So y negative 1.5 equals negative x positive 1.5. So y equals negative x plus 1.5, and we can transfer this negative 1.5 to the right side. So finally it becomes negative x plus 3. So we can easily see that we have the straight line y equals mx plus c, where m is negative 1. So that means the line that we have found is the tangent line y equals negative x plus 3. This is the tangent line to the curve x cubed plus y cubed equals 3xy at 1.5, 1.5 point. So let's see what happens. Y equals negative x plus 3. We are going to see the graph of this tangent line. So since this is the tangent line to this implicit function, it must touch the curve at a single point, 1.5, 1.5. So let's see. We can see that we have this blue colored straight line, and this is the tangent line. This line is acting as the tangent line. So for the curve x cubed plus y cubed equals 3xy, we have found the tangent line at 1.5 point. So this is how we can find tangent line. So up to now, we have learned how to find the derivative of explicit function, how to find the derivative of implicit function, and now we are going to talk about how to find the derivative if we have logarithmic or exponential function. So whenever we have logarithmic or exponential function, we may have the same explicit form, but in explicit form we have y equals f of x only, but for logarithmic or exponential function we have f of x with power g of x. So the power is also a function of x. So in that case, what we can do? So we have to know this one. So suppose we have y equals x power sine x, and the target is same. We are going to find dy dx. It is of the form f of x power g of x. So whenever we have this type of form, be sure that this type of functions are called logarithmic or exponential functions. Logarithmic function is the inverse of exponential function. Exponential function is the inverse of logarithmic function. But the thing is, how we can find the derivative from this type of functions? So first of all, we have to take logarithm on both sides. So what we are going to do, we are taking the natural log of y and the natural log of x power sine x. After taking the log of both sides, we have to now differentiate. So now let's differentiate both sides. d dx of natural log of y, d dx of natural log of x power sine x. Remember that from implicit differentiation, we have understood y is not constant. Y is y of x. So y is a variable. Y always depends on x. So whenever we have to differentiate this part, we have to think about the chain rule, whatever we have done in implicit differentiation. So on the right side, we have natural log of x power sine x. The reason behind taking logarithm is that we can easily use the logarithmic property. We know that natural log of a power b can be written as b natural log of a. So this is the property. Let's do the same thing here. d dx of sine x natural log of x, and in left side we have d dx of natural log of y. So our target is to find dy dx. You can see we are going to differentiate natural log of y in terms of x. So this variable and this are not same. So we can apply chain rule. We need to know what is the derivative of natural log of x. So natural log of x is 1 over x. So just consider y as x. So natural log of x, its derivative will be 1 over x. That is natural log of y, 1 over y, just like this formula. And the term that we have considered as x, that should be again in differentiation form. So this is what chain rule is. So on left side, we are done. On right side, we have u and v. So again, d dx of u times v is u d dx of v plus v ddx of u. So first sine x ddx of natural log of x plus natural log of x ddx of sine x. So 1 over y ddx of y. Previously we have seen that ddx of y is nothing but dy dx. So on right side we have sine x ddx of natural log of x. Now you can see that we have x in the parenthesis and ddx. Here we have also x. So that means now we can easily apply the direct formula. So ddx of natural log of x is 1 over x plus natural log of x. Now ddx of sine x, it is just cosine x, direct formula. Our target is to find dy dx, and we have already dy dx here, we can see. So let's just rearrange the right side so that it looks beautiful. So natural log of x cosine x. Now let's keep dy dx in left side, and if we try to convert this one to the right side, so it will be just y. So sine x over x plus natural log of x cosine x. So finally done. But we can also do one simple part, that is y is the same function x power sine x. In next step we can write dy dx as x power sine x, just we are keeping y as the main form. So sine x over x plus natural log of x cosine x. So done. This is how we can find derivative of logarithmic function. Sometimes you will see some functions which are known as parametric functions. It is not in the form y equals f of x. It is not in the form f of x comma y equals 0. But it is in the form x equals f of t. So x is a function of t, and y is also a function of t. So in that case, how we can find the derivative dy dx? So the function that we have here, x equals f of t and y equals g of t, is called parametric function. And the equations x equals f of t and y equals f of t are called parametric equations. So we have to know how we can find the derivative of parametric function. Suppose we have x equals cosine t and y equals sine t. So we have to find dy dx from these equations. So this is called parametric equation. So first of all, what we will do, at first we will differentiate this x part in terms of t. That means we are differentiating x in terms of t. Similarly, we will differentiate y in terms of t. So now you know that the derivative of cosine x in terms of x is negative sine x. So similarly, here we have cosine t dt. So that means this variable and this are same. So that means we can directly apply the formula. So derivative of cosine t in terms of t will be negative sine t by using the formula. So this is dx dt. It is done. Let's find dy dt. So here we are differentiating sine t in terms of t. Differentiation of sine t in terms of t will be cosine t. So it is dy dt. Now, our target is to find dy dx. So let's find dy dx. So dy dx can be found by this category. At first, try to understand the algebraic part. That is, if we write by this way, dy dx equals dy dt divided by dx dt. So if we simply calculate, that is dy dt, this part, times the division form is now written in multiplication form, then it will be dt x. So dt can be cancelled. We have dy dx finally. So that means this is how we can say that for parametric functions, we have to apply this formula, dy dt dx dt. So this is already in our hand, and also we have dx dt. So just we need to input the functions. So dy dt is found to be cosine t, and dx dt is negative sine t. So we can write this one as negative sine t. So finally done. We have found the derivative. So again, the question will be same. Find the tangent line if you have the parametric function that is defined by x equals cosine t and y equals sine t at some point. So first of all, you have to find dy dx, and then at a given point, find the value of this dy dx. That will be the slope m. So now we can apply y negative y1 equals m times x negative x1. We can also simplify the result. We know that cosine t negative sine t is cotangent of t. So in that case, we can say that dy dx equals negative cotangent of t. It is also the same result. So this is how we can find the derivative for parametric functions. Let's say we have another problem. X equals t squared and y equals t cubed. So again, our target is to find dy dx. So for that, what we have to do? We have to differentiate x in terms of t, and also y in terms of t. So dx dt will be dt t squared. So differentiation of t squared in terms of t is 2t. Differentiation of t cube in terms of t will be 3t squared. So we have found dx dt and dy dt. So it is easy to find dy dx now. So it will be dy dt over dx dt. That is 3t squared over 2t. So that means we will get 3 by 2 times t. So this is how we can find the derivative of parametric functions. So up to now, we have learned how to find the derivative of explicit function, implicit function, how to deal with logarithmic differentiation. We have learned how to find the derivative of parametric functions. So this is the time to focus on this point, that is how to find the derivative of inverse trigonometric function. So whenever we need to find the derivative of inverse trigonometric function, we can recall these formulas. So whatever formula you can see here, we have the same formula here. That is ddx of inverse sine is given, ddx of inverse cosine is given here, ddx of inverse tan, inverse cotangent, inverse secant, inverse cosecant, all the formulas are here. So these formulas are called the derivatives of inverse trigonometric functions. For example, you can see that differentiation of inverse sine is equal to 1 over square root of 1 negative x squared. So whenever we will try to find the derivative of inverse trigonometric functions, at that time, whatever process we have learned up to now, all that may be helpful, like chain rule, product rule, quotient rule, summation rule, subtraction rule. Everything will be helpful while computing the derivative of inverse trigonometric functions. Inverse trigonometric functions are also called arc function. Inverse sine is also known as arc sine. Inverse cosine is also known as arc cosine. So this is how we can think about all the inverse trigonometric functions. So now our target is to find the derivative of these functions. So let's say we have y equals inverse sine of x cubed. So we know that the derivative of inverse sine of x is 1 over square root of 1 negative x squared. That is, we know the formula ddx of inverse sine of x equals 1 over square root of 1 negative x squared. So the only difference between this and this function is here. In the formula we have x and here we have x cubed. So obviously we can apply chain rule. So for finding the derivative of this function means we have to find dy dx. So we are going to find the derivative of this function. That means dy dx equals ddx of inverse sine of x cubed. So we can see that derivative of inverse sine of x is equal to 1 over square root of 1 negative x squared. But here we have x cubed. So we can think about this one as x. That is, we can apply chain rule. So ddx of sine inverse x cubed will be 1 over square root of 1 negative x squared, like that. So that means here we have x cubed, so it is x cubed square. ddx of inverse sine of x cubed 1 over square root of 1 negative x cubed square. That means x cubed has been considered as x. So now we have to differentiate whatever we have considered. So we have considered x cubed as x. So we are going to differentiate this term again. So finally, from here, we can write dy dx equals 1 over square root of 1 negative x to the power 6. And we have derivative of x cubed. So we know that derivative of x cubed is 3x squared. So how we are getting derivative of x cubed as 3x squared? This is by power rule. ddx of x power n is equal to nx power n negative 1. So by this we can find the derivative of x cubed, that is ddx of x cubed So here n is 3. So nx power n negative 1. So 3x power 3 negative 1. So we are getting 3x squared. So this is how we have found here 3x squared. That means finally we have found the result. 3x squared over square root of 1 negative x to the power 6. So this is equal to the derivative dy dx. So this is how we can find the derivative of inverse trigonometric function. So let us consider another problem. Y equals inverse tan of natural log of x. So from here we need to find dy dx. That means we are going to differentiate the function inverse tan of natural log of x. So we know that the formula for inverse tangent of x is 1 over 1 plus x squared. So we can see that in the main formula we just have x, but here in the position of x we have natural log of x. So we can think about the whole quantity as x. Now we can apply chain rule. So ddx of inverse tan of x is 1 over 1 plus x squared. So ddx of inverse tan of natural log of x will be 1 over 1 plus x squared. So in the position of x we have natural log of x, and the term that we have considered as x, that should be again in differential form. So ddx of natural log of x. So now we can simplify, that is dy dx equals 1 over 1 plus natural log of x squared. So ddx of natural log of x, we know the formula directly, that is ddx of natural log of x is nothing but 1 over x. So this is 1 over x. So finally we are done. Our result is in our hand. So we have learned how to find the derivative of these functions like explicit, implicit, logarithmic or exponential, parametric and inverse trigonometric functions. So I think now it will be comfortable for you to deal with differentiation. That's all from me. Have a good time.